How often do you think about your heart health? Are you aware of the risks of cardiovascular disease? Well, let's dive into the heart of the matter. Cardiovascular diseases, encompassing coronary heart disease and stroke, claim the top spot as the leading cause of death in the United States. Particularly at risk are blacks and Hispanics in underserved communities. It's a sobering reality, isn't it? But there's good news. Cardiovascular disease is largely preventable. Stay tuned to learn how you can keep your heart beating strong. Heart Smarts, a health program, is here to empower you to live a heart-healthy lifestyle. This program is not just about information, but about transformation. It offers a comprehensive approach to help you understand and achieve heart health. Heart Smarts is committed to reducing the incidence of cardiovascular disease, the leading cause of death in the United States. The program focuses on underserved communities where the risk of heart disease and stroke is greatest. Through education and empowerment, Heart Smarts aims to turn the tide on these statistics. It's a call to action, a call to change, a call to live healthier, longer lives. Heart Smarts is about arming you with the knowledge and tools you need to make heart-smart choices every day. It's about the power of prevention and the promise of a healthier future. Remember, Heart Smarts is not just a program, it's a life-changing journey. It's about taking control of your health, one heartbeat at a time. But don't just take our word for it. Listen to these stories from people who have benefited from Heart Smarts. Imagine being told you're at risk for heart disease, a leading cause of death in the United States. Now picture having the knowledge and tools to combat that risk head-on. For people like Maria, a single mother from an underserved community, Heart Smarts was a beacon of hope. The program informed decisions about her heart health, ultimately reducing her risk of cardiovascular diseases. And then there's John, a middle-aged man who was once a prisoner of his poor lifestyle choices. For him, Heart Smarts was not just a program, but a lifesaver. It opened his eyes to the risks he was taking and gave him the push he needed to commit to a healthier lifestyle. These are not just testimonials, they are life-changing stories. Stories of empowerment, resilience, and triumph over heart disease. These are real stories from real people who have seen the impact of Heart Smarts in their lives. Are you ready to be the next success story? Your heart health is in your hands, and with Heart Smarts, you have the power to make a difference. It's time to take that first step towards a healthier lifestyle, a step that could redefine your future. Heart Smarts is not just an ally, it's a beacon, guiding you to make informed decisions for your heart health. So why wait? The path to a healthier heart is just a click away. You'll find the link to Heart Smarts right down in the description below. Start your journey towards a healthier heart today with Heart Smarts.
Ladies and gentlemen, today, I stand before you to delve into the fascinating world of concrete, a material that has shaped civilizations, enabled architectural marvels, and continues to be the bedrock of modern infrastructure. As engineers and physicists, we are intimately familiar with the profound impact that concrete has had on our societies, and it is imperative that we understand its intricacies and potential to pave the way for a sustainable future. Throughout history, concrete has played a pivotal role in the development of human civilizations, from the ancient Romans' use of volcanic ash-based concrete in the construction of aqueducts and colosseums to the modern era's utilization of high-performance concrete in skyscrapers and transportation networks. The evolution of concrete reflects the ingenuity and progress of engineering and physics. Understanding the material properties of concrete, such as compressive strength, elasticity, and thermal conductivity, has enabled engineers to push the boundaries of architectural design and structural innovation. At its core, concrete is a complex composite material governed by the principles of physics. The interactions between cement particles, aggregates, and water give rise to a heterogeneous microstructure that influences the material's mechanical properties and durability. Through rigorous experimentation and theoretical modeling, physicists have elucidated the underlying mechanisms governing the behavior of concrete at various length scales, from the atomic arrangements within cement hydrates to the macroscopic deformation of concrete structures under load. In the realm of engineering, Advancements in concrete technology have led to the development of specialized mix designs tailored to specific applications and environmental conditions, from self-consolidating concrete for intricate architectural forms to ultra-high-performance concrete for seismic-resistant structures. Engineers leverage their understanding of material science and fluid mechanics to optimize the performance and workability of concrete. Moreover, the integration of reinforcement techniques, such as steel rebar and fiber reinforcement, enhances the structural integrity and resilience of concrete elements, allowing for the construction of robust and durable infrastructure. As we confront the challenges of climate change and resource depletion, the quest for sustainable concrete solutions has become increasingly urgent. Engineers and physicists are exploring alternative binders, such as fly ash, slag, and calcined clays, to reduce the carbon footprint of concrete production. Additionally, innovative approaches, such as carbon capture and utilization, hold promise for mitigating the environmental impact of cement manufacturing. By embracing interdisciplinary collaboration and embracing holistic life cycle assessments, we can chart a path towards more sustainable concrete practices and foster a greener built environment for future generations. Concrete, in its essence, is a composite material whose properties are deeply rooted in both engineering principles and fundamental physics. The interplay between cement hydration and aggregate distribution, for instance, governs the material's strength and durability, drawing upon concepts of particle packing and intermolecular forces. Moreover, the evolution of concrete as a building material is intertwined with the history of civilization itself. Ancient civilizations, such as the Romans, utilized concrete in the construction of aqueducts, amphitheaters, and monumental structures, leaving behind enduring testaments to their engineering prowess. As engineers, we are continually striving to push the boundaries of concrete technology. Advances in materials science have led to the development of high-performance concretes capable of withstanding extreme environments, such as those encountered in offshore drilling platforms or nuclear power plants. Through meticulous experimentation and computational modeling, we gain insights into the microstructural behavior of concrete, enabling us to tailor its properties to meet specific performance requirements. Similarly, physicists play a crucial role in unraveling the mysteries of concrete's mechanical properties. By probing the material at the atomic and molecular levels, physicists elucidate phenomena such as creep, shrinkage, and fracture mechanics, laying the groundwork for predictive models and simulation techniques. Furthermore, the study of concrete's thermal and acoustic properties offers opportunities for interdisciplinary collaboration between engineering and physics, with implications for energy efficiency and urban noise mitigation. Beyond its utilitarian function, concrete serves as a canvas for artistic expression and cultural heritage. Sculptors and architects have long been captivated by concrete's sculptural potential, leveraging its plasticity and permanence to create enduring works of art. The fusion of engineering pragmatism with aesthetic sensibility is exemplified in iconic structures like the Sydney Opera House or the Guggenheim Museum Bilbao, where form and function harmonize in a symphony of concrete and steel. In the realm of sustainable development, concrete holds promise as a cornerstone of green infrastructure. Innovations such as carbon capture and utilization, CCU, technologies offer a pathway to reduce the carbon footprint of concrete production, while alternative binders derived from industrial byproducts promise to minimize waste and conserve natural resources. By embracing circular economy principles and life cycle assessment methodologies, we can chart a course towards a more regenerative built environment. Concrete embodies the convergence of engineering and physics, blending scientific inquiry with artistic expression, tradition with innovation. As stewards of this versatile material, it is incumbent upon us to harness its potential for the betterment of society and the planet. Through interdisciplinary collaboration, technological innovation, and a deep appreciation for its historical legacy, we can continue to build a future where concrete remains not just a material of construction, but a symbol of human ingenuity and resilience. Yet, as we marvel at the wonders wrought by concrete, we must also confront its environmental footprint. The production of cement, a key ingredient in concrete, accounts for a significant portion of global carbon dioxide emissions. As stewards of both science and engineering, it is our duty to mitigate these environmental impacts through innovative solutions and sustainable practices. In the realm of engineering, there exists a vast array of strategies to reduce the environmental impact of concrete production. One approach involves incorporating alternative materials, such as fly ash, slag, or silica fume, as supplementary cementitious materials. These byproducts of industrial processes not only reduce the reliance on traditional cement but also contribute to the reuse of waste materials, thus lessening the burden on landfills and natural resources. Furthermore, advancements in concrete mix design hold promise for enhancing both sustainability and performance. By optimizing the proportions of ingredients and adjusting curing methods, engineers can minimize the carbon intensity of concrete while maximizing its strength, durability, and resilience to environmental factors. This optimization process often involves sophisticated computational models rooted in physics principles, such as finite element analysis and molecular dynamics simulations, to predict material behavior and guide design decisions. Physics plays a pivotal role in understanding the fundamental properties of concrete and its interaction with the environment. For instance, physicists study the microstructure of concrete at the atomic and molecular levels to elucidate its mechanical, thermal, and chemical properties. Through techniques like X-ray diffraction, nuclear magnetic resonance imaging, and scanning electron microscopy, researchers can unravel the complex interplay between cementitious materials and aggregates, providing invaluable insights for material design and performance optimization. Moreover, physics principles underpin innovative approaches to enhance the sustainability of concrete structures. For example, researchers explore the use of self-healing concrete, inspired by biological systems, where embedded capsules containing healing agents react with water ingress to repair cracks autonomously. This self-healing mechanism relies on principles of diffusion, capillary action, and chemical kinetics, showcasing the interdisciplinary nature of concrete research at the intersection of engineering and physics. As we navigate the challenges posed by concrete's environmental footprint, let us draw inspiration from history. Throughout the ages, civilizations have leveraged the inherent properties of concrete to construct enduring monuments and infrastructures, from the ancient Romans' use of pozzolanic materials to strengthen their concrete structures to the modern era's adoption of reinforced concrete for high-rise buildings and transportation networks. The evolution of concrete reflects humanity's quest for innovation and resilience. In the quest for sustainable concrete solutions, let us heed the lessons of the past, leverage the power of engineering ingenuity, and embrace the principles of physics to pave the way towards a brighter, greener future. Fortunately, the field of concrete research is brimming with promise. Engineers and physicists around the world are exploring novel materials, such as geopolymers and alkali-activated cements, which offer reduced carbon footprints compared to traditional Portland cement. Geopolymers, for instance, leverage the chemical reactions between aluminosilicate materials and alkaline activators to form a strong, durable binder without the need for Portland cement. This process not only reduces carbon emissions but also mitigates the environmental impact associated with limestone quarrying, a primary source of raw materials for cement production. Furthermore, advancements in nanotechnology hold immense potential for revolutionizing the properties of concrete. By incorporating nanomaterials such as carbon nanotubes or graphene oxide, engineers can significantly enhance the mechanical strength and durability of concrete structures. These nanomaterials act as reinforcement agents at the nanoscale, effectively bridging microcracks and improving the overall toughness of the material. Moreover, nanotechnology enables precise control over the hydration process of cement particles, leading to denser concrete with reduced porosity and permeability, thereby enhancing its resistance to environmental degradation and extending its service life. Delving into the physics behind concrete, it's essential to recognize the fundamental principles governing its behavior. Concrete is a composite material composed of aggregates dispersed within a cementitious matrix. Understanding the interplay between these components and the forces acting upon them is crucial for optimizing concrete mix designs and predicting structural performance. Physicists employ mathematical models and computational simulations to analyze the complex interactions of particles, fluids, and forces within concrete, enabling precise predictions of its mechanical properties and behavior under various loading conditions. Moreover, historical insights shed light on the evolution of concrete as a cornerstone of human civilization. Dating back to ancient times, civilizations such as the Romans utilized rudimentary forms of concrete to construct enduring structures like the Pantheon and aqueducts. The development of hydraulic lime and pozzolanic materials allowed for the creation of durable mortars and concretes, laying the groundwork for modern construction techniques. Over the centuries, advancements in materials science, engineering methodologies, and construction techniques have propelled concrete to the forefront of global infrastructure development, shaping the skylines of cities and connecting societies across continents. As we navigate the challenges of the 21st century, the role of engineers and physicists in shaping the future of concrete cannot be overstated. It is incumbent upon us to harness the wealth of knowledge and technological innovation at our disposal to develop sustainable solutions that mitigate environmental impact, enhance structural performance, and ensure the longevity of our built environment. By embracing interdisciplinary collaboration, pushing the boundaries of scientific inquiry, and upholding the principles of ethical stewardship, we can pave the way towards a more resilient, sustainable future for generations to come. Moreover, the integration of digital technologies into the realm of concrete represents a convergence of engineering ingenuity and computational prowess. With the advent of artificial intelligence, AI, and machine learning algorithms, we are now able to analyze vast data sets, identify patterns, and optimize concrete mix designs with unprecedented precision. By harnessing the power of physics-based simulations and computational modeling, we can simulate the complex interactions between materials at the molecular level, enabling us to predict material behaviors and optimize performance parameters. This symbiotic relationship between engineering and physics not only enhances our understanding of concrete mechanics but also empowers us to push the boundaries of innovation in materials science and structural engineering. In tracing the historical trajectory of concrete, we uncover a narrative rich with engineering triumphs and scientific breakthroughs. From the ancient Romans' pioneering use of pozzolanic materials to the invention of reinforced concrete by French gardener Joseph Meunier in the 19th century, the evolution of concrete has been intertwined with human innovation and technological progress. Today, as we stand on the shoulders of our predecessors, we are tasked with pushing the boundaries of what is possible, not only in terms of structural performance but also in terms of sustainability and environmental stewardship. The principles of physics underpin every aspect of concrete production and performance, from the hydration process, where cement particles react with water to form a crystalline matrix, to the mechanics of load-bearing structures, where forces are distributed and dissipated within the material. The behavior of concrete is governed by fundamental laws of physics. By applying principles such as Newton's laws of motion, Euler-Bernoulli beam theory, and Darcy's law of fluid flow, physicists and engineers alike can unravel the complex interplay of forces and phenomena that shape the properties of concrete. As we look towards the future, the imperative to build smarter, safer, and more sustainable infrastructure has never been more urgent. In an era defined by rapid urbanization, climate change, and resource scarcity, the need for innovative solutions has never been greater. By harnessing the collective power of engineering creativity, scientific inquiry, and technological advancement, we can pave the way towards a brighter, more resilient future, one where concrete serves not only as a cornerstone of our built environment but also as a symbol of human ingenuity and stewardship. The journey ahead will undoubtedly be challenging, but it is also filled with boundless opportunities for discovery and transformation. As we continue to push the boundaries of what is possible, let us remain steadfast in our commitment to excellence, integrity, and sustainability. Together, let us embark on this journey with curiosity, courage, and a shared vision of a world where concrete and the ideas it represents truly stands the test of time. However, our journey towards a greener, more resilient built environment extends beyond technological innovation. It requires a collective commitment to responsible stewardship and ethical practice. As engineers and physicists, we must advocate for sustainable design principles, promote interdisciplinary collaboration, and prioritize the long-term well-being of both people and planet. In the realm of engineering, sustainable design principles are paramount. This involves optimizing concrete mix designs to minimize environmental impact, such as reducing cement content or incorporating supplementary cementitious materials like fly ash or slag. Physics comes into play here as well, as understanding the properties of these materials at a fundamental level allows us to predict their behavior in complex structures. By leveraging principles of thermodynamics, mechanics, and material science, we can develop concrete formulations that not only meet structural requirements but also contribute to a more sustainable future. Interdisciplinary collaboration is key to addressing the multifaceted challenges posed by concrete production and construction. Engineers, physicists, chemists, and environmental scientists must work together to develop holistic solutions that consider not only the technical aspects but also the broader societal and environmental implications. By integrating diverse perspectives and expertise, we can innovate more effectively and ensure that our solutions are both technically sound and socially responsible. Furthermore, history serves as a valuable teacher in our quest for sustainability. The ancient Romans, for example, were master builders who utilized concrete extensively in their architecture, leaving behind enduring monuments such as the Pantheon and the Colosseum. Studying their techniques not only provides insights into the durability of concrete but also highlights the importance of long-term thinking and resourcefulness in engineering practice. Drawing inspiration from the past, we can reimagine concrete for the modern era, imbuing it with sustainability and resilience for the challenges ahead. As we look to the future, the imperative to prioritize the long-term well-being of both people and planet has never been more pressing. By embracing sustainable practices, fostering interdisciplinary collaboration, and drawing upon the lessons of history, engineers and physicists can lead the way towards a greener, more resilient built environment. Together, let us rise to this challenge with courage, creativity, and a steadfast commitment to a better tomorrow. In the realm of engineering, concrete stands as a cornerstone of structural design, offering unparalleled strength and versatility. Through careful manipulation of its composition and curing processes, engineers can tailor concrete to meet the specific requirements of diverse applications, from high-rise buildings to transportation infrastructure. By leveraging principles of mechanics and materials science, we optimize mix designs, analyze structural behavior, and ensure the long-term performance of concrete elements under various loading conditions. Moreover, the study of concrete provides a fertile ground for exploring fundamental principles of physics. From the microscopic interactions between cementitious materials to the macroscopic behavior of reinforced concrete structures, physics elucidates the underlying mechanisms governing the properties and performance of concrete. Concepts such as elasticity, viscosity, and thermal conductivity come to the forefront, guiding our understanding of how concrete responds to external forces and environmental factors. Delving into the annals of history, we uncover the enduring legacy of concrete as a testament to human innovation and resilience. From ancient Roman aqueducts to modern megastructures, civilizations throughout the ages have harnessed the power of concrete to overcome engineering challenges and leave an indelible mark on the built environment. Each era has contributed its own advancements and innovations, shaping the evolution of concrete into the versatile material we know today. In conclusion, concrete epitomizes the intersection of engineering and physics, a material born from scientific inquiry and refined through human creativity. It is our privilege and our responsibility to harness the power of concrete to build a better world for generations to come. Let us embrace this challenge with resolve, imagination, and a steadfast commitment to innovation. Thank you.